Hi everyone, so let's go ahead and get started with the Pset solutions for our first problem set. So, started off with this one, draw the Lennard-Jones potential as a function of atomic distance, where atoms repel, attract, where is the equilibrium distance, where is the force maximized. So, I know that my Lennard-Jones potential looks something like this. Okay, so I've got right here, here. So this is my equilibrium distance right here. Here atoms will attract. Here atoms will repel. And then this is my equilibrium distance, and then that inflection point is where my force is maximized, because I know that my force is minus the gradient of my potential. So essentially, my force is equal to the negative, basically d u L Lennard-Jones divided by dr. When I set that equal to 0, so I know that my force is maximized when my second derivative is equal to 0, so where my curvature changes from positive curvature here to here, this inflection point, negative curvature there. You can also do this and prove this kind of mathematically here. So let's go ahead and let's look actually at our Lennard-Jones potential, which we happen to have handy right here. Fantastic. So let's open up Mathematica for the first time, and we'll probably be doing that for quite a bit of time as well. So let's go over here, and we could see that my Lennard-Jones potential, so ULJ is equal to 4 times epsilon, and then sigma divided by r to the 12 minus sigma divided by r to the 6th. I could find this, my ULJ, so I could actually find, if I want to find my equilibrium distance, actually I know that my force is equal to minus derivative of ULJ with respect to r. So if I want to find my equilibrium distance, d ULJ with respect to r, solve for when this is equal to 0. Oops. Solve when this is equal to 0. And you could see some answers here, and then I could also do the same thing for force as well. So let's go here, let's go there. So let's do force. And if we plugged in for those parameters, we get numerical answers. But we can kind of see how we're going to solve and actually how we're going to go about solving the problem. And actually, that leads us to our next problem right here, which is one of, we discussed several potentials in class, ubiquitous being Lennard-Jones potential. I asked one to run a simulation for copper. So we assigned a value for copper of, for example, and actually I'm going to go ahead and just go up here. So let's go ahead and reevaluate kind of everything. So I've decided here that epsilon, for my particular example, is equal to 0.135 eV. My sigma is equal to 2.814 angstroms times 10 minus 10. I'm just going to change my units just to make sure. Always SI units, that'll make life easier. And his results are one, and ask you for these parameters. What will be the equilibrium distance between copper atoms? What distance the force maximizes? Confirm your answer below, above. What might explain the difference? So we need to figure out what is our equilibrium distance, and then what is our maximum force, and then see if that matches what we know about copper. So force I know is this. So I'm going to solve here. So my equilibrium distance is 3.15 angstroms. So if I go ahead and look at copper, I'm going to do it in our friendly little notebook. So I know that I could use my periodic table, my handy periodic table here, to figure out this is my metallic radius, that second one from the bottom here, or the top, excuse me. So if I look at copper, for example, for copper, my metallic radius is 1.28. So I know that my equilibrium distance is when when an atom is 2r away from one another. So my equilibrium distance is 2r, so 1.28 times 2. Something is going a little bit wrong. I know that looks like a small difference, but atomically that is a very significant difference. So what's happening here? Also, let's look at where the force is maximized. So we go here, we solve for the force, this value right here, so 3.5 times 7 minus 10. So what's happening? What's the difference? Well, this is a Lennard-Jones potential. So we shouldn't use Lennard-Jones potentials for metallic interactions. So we need to use more complex potentials in order to kind of get our, our estimated value. All right, let's look at a new potential here. It's actually used to solve, or actually kind of basically model ionic interactions. So let's go ahead and look at our potential. So nu u, un, for nu, ui minus e, basically e squared. I'm going to put lots of parentheses. This is probably going to infuriate people, but I like to be a little safe. 4 times pi times e naught r plus b divided by r to the 8. So E is my electronic charge, which is 1.602 times 10 to the minus 19. Let's see if that is in fact the case. Let's go back to our lecture notes. We could look at some little potentials here. Look at it here. I think it's on the next page. Yep, 1.602 times 10 to the minus 19 coulombs. 19, not 10. So that's actually a good check. So here we go. And here we go. Oops, not negative, negative. There we go. And then we know that our E naught, I think, is also given in the problem set. So our permittivity of vacuum. So my permittivity of vacuum is 1.5 eV. So my UI, excuse me, UI is equal to 1.5 EV. And I also know that my permittivity of vacuum, I'm going to look that up. My permittivity of vacuum is going to be, let's see, 8.854 times 10 to the minus 12. Go ahead and put that over here. And there we go. So we have, and we could actually do a quick unit check. So actually, let's go ahead and just double check. So our Faraday constant here. So let's go back over here. So we knew that this is going to be our Coulomb squared divided by Faraday, and a Coulomb per Faraday, or Coulomb squared per Faraday is equal to a joule. So we're excellent, right? Actually, we're very, very, very good there. So that's going to be in joules. We're going to actually really be careful with that in just a second, so that we make sure that we're all in our kind of correct units. So I'm actually going to go ahead right now and change that electron volt there to an EV. So, as we know, Coulomb squared per Faraday is a joule. So I'm going to go from EV to joule conversion. So I'm going to do 1.602 times 10 to the minus 19. So I'm going to do that right now here. Just do that times E. So now I'm okay. So we've got everything essentially that we do. Now let's go ahead and let's ask, what is the problem actually asking us to do? So we're also told that the equilibrium distance is 2.78 angstroms. So basically I know that when I take the derivative of un with respect to r, and I'm going to solve basically, I know that here, when I set this to the equation to 0, so I'm going to take this out. So I know that this is equal to 0. Or actually, I'm going to substitute here. So this is my derivative. Oops. Deriv. So I'm going to do deriv slash dot r goes to 2.78 times 10 to the minus 10. That is my equilibrium distance. So we have taken the derivative here. We know that this value, the derivative of my potential, should be equal to 0 when I make my equilibrium distance. We're told in the problem the equilibrium distance is 2.78 angstroms. So I'm going to go ahead and solve for B. Solve. This whole thing should be, let's go ahead. Let's see if this works. Sometimes it doesn't. Oh, there we go. And what are the units here? Joules meter to the 8th. So there we go. So we've got our B. So I'm actually going to go ahead and define that now. So B is equal to this. And then now we could have our potential. We've got everything again. Now these are in units of, everything's in joules. So we are good to go. We've done the conversions. We're fine. So what distance is the force maximized? The force is equal to clear. Seems to be clear. Yeah, force was determined from up here, so I'm going to make sure to clear force. But I know that my force is going to be equal to minus derivative of un with respect to r. So we've got that. So I'm going to do when is my force maxima, or what distance? So derivative, solve derivative force with respect to r, and then set that equal to 0. So we see that the value is going to be at approximately 3.44 angstroms. Then the question asks, what is the energy at this point? Well, so I'm going to do un slash dot r goes here. There we go. That's my energy in joules. What is the value of the force at, so that's the energy. What is the value of force at 3 angstroms? So I could go again, 4 slash dot r goes to 3 times 10 to the minus 10. What is the potential energy at a value of 1 angstroms? So un slash dot r goes to 1 times 10 to the minus 10. What is the energy at the equilibrium distance? Again, un slash dot r goes to 2.78 times 10 to the minus 10. And then what is the force at this distance? So force slash dot r goes to. So again, you see here that the energy is always kind of low here. Again, 3 angstroms high. So again, we can kind of see where the force values are going. It should never be lower than this. So force at 2.78 to the minus 10, and basically nil there. All right, which makes sense. Now, let's get into some directions and planes and all kinds of fun stuff here. So, what type of unit cell is represented in A, B, and C? Excuse me for the typo. How many atoms in each unit cell? What's the atomic packing factor for each unit cell? So, A, B, and C, atoms, and atomic packing factor. So, A, this is going to be BCC. This is FCC, and this is simple cubic. There are 2 atoms, 4 atoms, 1 atom. And for the atomic packing factor, this is 0.4. I believe this is pi over 6, but it's basically less than 0.74, less than 0.74. Again, you can calculate that out. We've done that in class. The calculations are in the notes. So you can kind of double check those there, and I will double check it when I'm grading our problem sets. All right, so 4 is done. Are there any close packed directions in A? So let's go ahead. Are there any close packed directions in A? I don't necessarily. Actually, we see one close packed direction if we go from here all the way to across from right there. So this is a close packed direction. Everything else is not. So, and that is the, just to kind of do it, 111 direction. Fantastic. So let's see what other questions are being asked here. Oops, let's go down a little bit. So, are there close back directions in A? What are the close back directions in A, B, and C? So, let's see. So, our close back directions for A is basically this family of the 111 directions. For FCC, it's the 110 family directions. For simple cubic, 100. So, those are our close packed directions. Let's go ahead and see here. It's asking, is 110 a close packed direction in C? No, we just proved that right there. And then we can explain why not, because again, we're going through distances where the atoms aren't touching. All right, let's go ahead. I'm going to kind of erase here. And let's go ahead and let's look at what other questions are being asked here. Oops. Excuse me. Oops. This is a little bit sensitive. Sorry for the kind of head juking. Calculate the planar density of the plane in B. What is the planar density for 001, and what about 110? All right, so let's look at the planar density, and actually we need to figure out what is the plane. Well, actually, let's just calculate the planar density here. So I need to calculate the planar density in the plane in B. So here we see I have a plane essentially that looks like this in B. So it looks like this, where this is A, and this is A square root of 2, where A in FCC is equal to 2R square root 2. So I see that I have atoms at the corners here, and I have an atom that goes to the sides. So I have quarter, 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 half, half. So there are 2 atoms per plane. So my planar density, so go ahead and go down to here. So this is my AFCC. So my A for FCC is equal to 2 times R times the square root of 2. And here in this particular problem, my PD is going to be number of atoms times 2 times, what's the area? 2 times pi, 2 times, actually, times pi times R squared. I'm going to take this, planar density is here, divided by, what's the area here? AFCC times A times A, actually AFCC times square root of 2. It better be less than 0.9069 because I know this is not a closed packed plane, and well, it is not. So that is my planar density here for B. Well, let's see what the other questions are. Oops. Planar density. What is the planar density of OO-1 in B and A? So if I'm looking at B, my OO-1, I'm going to actually redo, this is going to be my, this is going to be my new origin for B and A. So this is my new origin here. So if I go ahead and draw that, my OO1 is just going to be, actually, this backward plane right here. So in B and in A, I believe that's what's being asked here. So if I look at B, again, I'm FCC. So this is A, this is A. I have atoms at the corners. I also have atoms right at the center. So again, I have how many atoms? 2 atoms here. So the only thing that changes here would just be removing the square root. And I'm still not close packed for the plane, which makes sense because it's not close packed. So same kind of idea there for BCC, except remember that my A for BCC is equal to my OO1 for BCC would look like this. Atoms at the corners, that's it, because the central atom's in the center. So A for BCC is 4 times R by square root. So I would have 1 atom, so pi times R squared divided by A BCC times A BCC. And let's look at that numerically. And what do you know? It's less than. So we've got it. So let's continue here with what the question, I think, then asks. We have one more plane to look at. What about 1, 1, 0 in B and C? So now we're looking at B and C and minus 1, 1, 0. So I'm looking at this plane B and C. Looking at minus 1, 0, 0. I'm just going to erase here at this point. So again, I'm going to take my origin and draw. Actually, I'm going to draw it in green. So this is going to be my new origin. So I'm going to pop out here, pop out here. So I'm going to have basically a plane that intersects over here. This point here, here. So 1, I think the plane that they're asking 1, 1, 0. So then it's also going to intersect essentially here. This is my new origin here. So again, let's look. So we're going to intersect 1 there. We are going to intersect here. So actually, we'll get the plane. Oops, 1 second here. We are back. So we are trying to, excuse me, sorry, I had to step out for just a second. Oops, let's go a little slower here. So we're trying to figure out what is the planar density of 1, 1, 0 in B and C. So what we're going to do here, we renamed our origin here, so we're going to have an intersection point right here. We're also going to have an intersection here, and then that's going to be our plane. Same thing in here. Very similar, except right here. So if I'm looking at B, I'm going to have a plane that looks like this. I have a side here that is A. This is going to be A root 2 again. I have 1, 2, 3, 4. And then I have an atom here and an atom here. So again, quarter, 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 half, half. So I actually have the same planar density as actually this one right here. Except for, remember, we had that square root 2. So square root 2. Here. And then for C, I have a very similar looking cell, just 1 atom. And again, this is simple cubic. So for my A of simple cubic, so my A of SC is equal to 2 times R. So there's my ASC. So this is A here. This is A, this is A, and this is A square root 2. So I only have one atom there. So now what we're going to do is do pi times r squared divided by, so one atom times the cross-sectional area there times the area of my plane, which is going to be ASC times ASC times square root of 2. Look at this. Better not be close packed, and it's not close packed. So that is, or those are our planar densities. Now we're asked to draw essentially the series of directions here. So the 1, 1, 0 in our empty unit cell. So let's do 1, 1, 0. So I'm going to do 1, 1, 0. So I'm going to draw that. So that's my 1, 1, 0 direction right there. So that is 1, 1, 0. I need to also draw negative 1, 0, 1. So let's go ahead and draw that. So negative 1, 0, 1. 1. And so let's go ahead and actually let's deduce that one. I'm going to do 0. Actually, I'm going to do 0. I'm going to do in the plane. So 1, 0 minus, I'm going to do 1, 1. And then, actually, excuse me, I need to make this a 1. So this is 1, 0. So this is my finish. This is my start. So that's going to give me 1. That's going to give me 0. That's going to be giving me 1. So I can draw that here. So my start is actually right here at 1, 1, 0. My finish is going to be actually 0, 1, 1. It's going to be like this. So I could start there. Start right here, 1, 1, 0. I could finish at right there. So, again, fairly, hopefully, a little bit straightforward. What's the next direction here? The next direction we are asked for is 1, 2, and minus 2. So, 1, I'm going to erase here. I'm just going to keep it 1, 2, and minus 2. So again, now the 2's are involved, so I'm going to have to do, this is going to be basically, it's going to be a half. So 1/2 times, actually, this will be 1, and this will be 0, minus, this is my finish, so my start is going to be 0, 0, 1. That should give me a half, 1, and minus 1. And when I multiply those, so again, that direction. So my finish is my start. So my start will be 0, 0, 1 here, and I'm going to end at a half, 1, 0. So I'm going to go all the way over here. There you go. So you kind of hopefully get the picture now, but let's go through the rest of these. So 1, 2, 2, how about 301? So that's do 301. Let's do, I'm going to switch to red here. So 301. Let's draw 301. So I'm going to do my finish. Let's see. I'm just going to do, let's say 1, 1, and then I'm going to do a third, and then let's do 0, 1, 0. So that should leave me with 1, 0, third, multiply by 3. Okay, so this is my finish, this is my start. So I'm going to do my start at 0, 1, 0, and then at 1, 1, and then a third. So from here to here. So start and finish, just like that. All right, let's get to the next one. Oops, sorry about that. Let's get to the next one here. Keep these basically braces. I should have kept the braces. It's all right. So let's look at the next one. So we have 301. Let's do 2 minus 1, 3. So 2, 3. So let's go ahead and take a peek at this. So this will be Basically, let's see what to do. Split by 6, so 6. This will be 0, and then 2, 6, and then 0, 1, 0. So that will leave us with half minus 1. Oops, I needed this to be, actually I need this to be 1/6. So 1/6 hat, and then we're going to do, ooh, shoot, second here. Actually 2, 6. So 6. So actually this needs to be, excuse me here, doing these lines. So 2 over 6, 3 over 6. So this is going to leave me with, let me get here. So this is going to be 2, 6. This is going to be 1 over hat 6, and then 6. Multiply that by 6, and then I'm going to get the values out there. So let's go ahead and write these down. So my start, 0, 0, 6. Then, for example, I'm going to go to basically a third here, 0, and then go up to a half. So right here, something like that. Again, show your work. Make sure we get these guys right. All right, almost done. And then 2 hat 01. All right, 2 hat 01. 2 hat 01. So I'm going to do, this is going to be my 0, 1, 1, 1, and then this is going to be 1, 0. This should be okay. Actually, one of these is going to have to be, this is going to have to be a half. So let's go ahead and bring this down here. So this is going to be 1 hat 0 half. So it's going to give us 2 hat 1. So let's go ahead and draw it. So 1, 1, 0. Start there. Finish at 0, 1 half. There we go. Actually, I think that one is repeated. Nope, we're okay. All right, that's it. So we are done with directions. So we finished the direction one. Whew, that took a little while, but anyway, we're almost there. All right. So I'm going to go ahead and write these down right now in this page so we can see it. So 0, 1 hat 1. So 3, 1 hat 2 hat. 1, 3, 0. 0, 0, 3 hat. And then 0, 3 hat. All right. I think that's pretty much it. Good. So I'm going to do this one first. So let's go. Those are my HKLs, my indices, my intercepts are the inverse. So my x-intercept is 1, 1/3, and 0. So 1, 1, oops. So 1, and then a third. So it's going to go like this, this. There we go. So that is that one. That erased. Now let's do the negatives. Whenever you have a negative, you're going to have to do a new coordinate. So I'm going to go ahead and pick, this is my new coordinate system. So this is my new origin, coming out here, coming out here, coming out here. So I'm going to go ahead and go, oops, actually, since we're here, I'm going to go ahead and take my origin, like right here. So out, and there we go. So -1, and then here it's going to also pick at 1 right here. So this is going to be, so here it is, -1. So first off, I'm parallel here, so I'm never cutting through. -1, 1, got it. So that one's done. Let's do 0, 0, 3. So my intercepts are basically -3rd. So I'm going to pick my origin here, and then it's just going to be basically going down to a third. So smelling this. There, got that one. Let's do 103 hat, I think. Must be. Yep. So 103 hat, again, I'm going to pick something right. Actually, I'm going to do my origin like this. So my origin, my x. So my x-intercept is 1. And then my y-intercept is minus a third. So right here, minus a third. So it's going to be like this. This. You get the picture. And then finally, let's go ahead and get our last one in here. I just erased it, but it's cool. So 3 hat, so again, a third, minus 1, minus half. So I'm going to pick my origin as follows. So I'm going to go ahead and pick my origin. Actually, let's go right here. It's a little bit difficult one where I have to pick. So you may pick it back here. Actually, right here. So we can go third, and then we can go. Yeah, actually, we're going to pick our origin right here. So this is our origin. So we're going to go a third. We are going to go, again, minus 1. So right here. And then we're going to go down a half. So like this. So it's going to be something like this, this. There you go. So we've got it. Now, I'm interviewing at D Project and actually Project D. Yeah, D Project, and they give me the following RDF PDF graph. What type of material am I working with? What is the integral of the first peak? What is the actual material? What element? Draw semicrystalline amorphous polymer PDF RDF. So I know that the PDF RDF. So our PDF RDF. So our GFR. So for a semicrystalline polymer, I'm going to see more spikes. For an amorphous, it's going to be broader. So essentially, so those are the difference there. So again, semicrystalline polymer is going to have more long-range order, less short-range order. So actually, our semicrystalline polymer will look like this. I'll have one peak and then dead. See here, we have all these peaks, and they're going to continue. Not as sharp as metals, obviously, but so this is for sure a metal. Now, I know for my RDF PDF, this is my nearest neighbor distance, so 2R equals 2.72 angstroms. If I can figure out my metallic radius, and I can also figure out what type of material this is. So the second number, that 3.14, is the next nearest neighbor distance. So 3.14 divided by 2.72. I know that my nearest neighbor distance, or my nearest neighbor distance is always 2R. And then in a FCC crystal, it's 2R divided by 2R times, actually. 2R times square root 2 divided by 2R. 2R. And let's look at that value here. And this ratio is not correct. But I also know that for an BCC structure, for our, let's see, my next nearest neighbor distance is 4R times divided by square root of 3, divided by 2R. Not money sign, R. Divided by 2R. And let's look at this. The ratio is pretty much identical here. So this material is BCC. So it's a BCC material. The integral of this first peak is the number of nearest neighbors, which for BCC is number of nearest neighbors. And I know that my 2R is equal to basically 2.72, so 2.72 divided by 2. So I'm looking for a BCC material that has a metallic radius of 1.36 angstroms. So what BCC material has a metallic radius of 1.36 angstroms? So 1.36. This thing's not it. 1.37 PD. 1.36. There's a couple of close ones. Actually, but I think I'm maybe misreading this chart. Hold on a second. I think BCC is, those aren't BCC, excuse me, those are FCC. The body center ones are the other ones over here. So those aren't, definitely not it, because those aren't even BCC. But let's look over here. All right, so we're looking at 1.3. Looks like chromium once, oh no, vanadium. Vanadium looks like to be our candidate. Look at that, metallic radius 1.36 BCC. So I'm pretty sure it's vanadium. So I like that answer. So let's go back to our problem set. Great. Now, the last question is basically saying that we're given these files. So we have 4 Excel files, and we have the concentration of vacancies, and we know that we have an expression, XV equals exponential minus QA divided by T, and that's essentially our concentration of vacancies. So we have concentration of vacancies, T. I know that if I take the natural log, XV equals minus QA divided by K times T. So I have a list of temperatures, I have a list of XV. So if I basically plot ln XV by 1 over T, I can figure out and calculate what essentially I could calculate the activation energy in joules. As we increase the concentration of vacancies, entropy increases because again we have more spots than available to move in. So let's go ahead and play around with those values. So let's go ahead. I think I've already downloaded it. Yep, 1, 2, 3, 4. So I'm going to copy these. I'm going to go into here. And I'm going to go into here. So list, data list is this. So here we go. So it's going to be 3, 2, 1, 4. Very intuitive. So I'm going to import list 1. Let's look at the data, how it's done. I'm going to flatten 1. Comma 1. So I'm also going to do one more. There we go. So I'm going to do all 1. So these are all my concentration of vacancies. So I'm going to do the natural log. Log is this. If I was doing log base 10, then I do that. So that's the log. So this is my basically XV. And I'm going to do a table. So I'm just going to loop over for this for all of them. I from 1 to length list. And then let's go ahead and close that up. And then I'm going to do, so that's my XV, well, it's ln XV. I'm going to actually do that. ln XV, so 1 over T, I'm just going to do OT, equals kind of the same thing. Copy this. Except I'm going to take apart the second element, and instead of log, I'm just going to do 1 divided by. Should work. Alright, that should be good. So, now I can do transpose, and I'm going to do OT, OT1, T1, then ln XV 1, and then I'm going to do fit 1, X. Let's see. I don't think it likes the indeterminate values, so I may take it. I may do a linear fit by hand, or I may just take like the 5 to -1. Yeah, let's take a peek at this. So, how about 10? All right. So let's see if it works with 10. I think it will. Yeah, it just doesn't like the indeterminate points. So this is my slope. So this slope is equal to, and actually, so our K is going to be in 1 point, because we need it in joules, 1.38 times 10 to the minus 23. So I need to solve minus QA over K equals this. So that's my activation energy. I can do the same thing here for Actually, we may be able to do this very intelligently. Length of OT. Great. So now I could also pick, so these are my fits. I could do probably fits 1. How about fits 1, 2, divide this by x, and then I could do, solve minus qa divided by k equals this. And I could do that as a table. I could do this. So fancy. Isn't Mathematica so nice? Elegant solutions. It's voila! That's it. That's our problem set in a nutshell. So I hope that's been helpful. Again, hopefully this video will be helpful in kind of looking through your problem sets and kind of looking back and understanding your grade, and more importantly, kind of learning again, how do we attack each of these problems? These are, again, more fundamentals for when we get into the crazier and fun stuff. So I look forward to seeing you in the next video. Thanks.